In this video, we will consider conditional probability. In some circumstances, we need to calculate the probability that something has occurred, given the knowledge that some other event has already happened. This type of probability is called conditional probability. So in this example, we need to consider a bag of marbles that begins with 2 blue marbles and 3 red marbles. Let's first ask our original question. What would be the probability of drawing a blue marble from the original bag? So we recall the original bag had 2 blue marbles and 3 red marbles. And we know probability is the number of ways what we're looking for could occur, so the number of ways I could draw a blue marble, divided by the total number of options. So as there are currently 5 marbles in the bag, we know the total number of options is 5. And there are 2 blue marbles that I could have drawn and met the goal of drawing a blue marble. So our original probability of drawing a blue marble is 2/5. Next, we're asked, again, what is the probability of drawing a blue marble after we've drawn 1 red marble from the bag? So what's happened is we had our original bag, we took out 1 of the red marbles, and now this is what remains in the bag. So 1 of the 3 red marbles is gone, therefore we only have 4 marbles left in the bag, and we know it consists of 2 blues and 2 reds. So now when we calculate the probability, since 1 marble has been removed, that's going to affect our total number of marbles in the bag. For instance, there's no longer 5 marbles in the bag, but 4. 1, 2, 3, 4. And since we know that 1 of the red marbles was removed, there's still the same 2 blue marbles there that were originally present. So the number of ways we could select a blue marble is still 2. This was our first example of a conditional probability. We are calculating the probability that we would get a blue marble after we knew that 1 red marble had been removed from the bag. Now, in our next example, we are supposed to suppose that based on the original bag, we've now removed 1 blue marble. So now we're in this situation. So we originally had 5 marbles, 2 blues, 3 reds. We knew that 1 of the marbles was taken away from the bag, and that was specifically a blue marble. So the remaining bag only has 4 marbles. 1 of them is blue, the other 3 are red. So if you would take a moment to write out what is the probability that we draw a blue marble from this new bag. Well, there's 4 marbles that we could have drawn from, and of those 4, only 1 of them meets our criteria of being a blue marble. Now there is a formula for a conditional probability, and as we go through our future problems, I'll try to show 2 different ways to solve the problem. Often for our class, conditional probability problems can just be thought about, and you ask yourself, if this happens, what happens to what was going on? How does that change my probability? And I think that kind of method is generally easier to work with, and I'll try to illustrate that in our future examples. But if that method does not work for you, then you can always use the formula. So the way conditional probability works in terms of the formula is, let's talk about the notation first. This P we know stands for the probability. And it's the probability of this expression, capital B, vertical line A, and that stands for the probability of B given A has already occurred. And the probability that B would occur given A has occurred could be found as the probability that A and B occur divided by the probability of A. So notice the pattern here. The thing that has already occurred, we have to put its probability in our bottom of the fraction. So let's turn to our next example, and we will calculate the conditional probability in two ways. We'll calculate it in the first way I described, just kind of thinking about the situation. And then for additional practice, we will calculate it using this formula, and we'll see that we get the same answer either way. So here we have a sample space. We know the phrase sample space is just the idea of in our probability calculations, it's all the possible outcomes. So our sample space is the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And what's described is that we're going to select a single number at random. So maybe the way we can envision this is we have some bag, and then we have our tiles with the different numbers in the bag, and we know that we are going to randomly select one of the tiles. So each tile has an equal likelihood of being selected. So we'll only select one. Now we're going to calculate the probability of the given events. So event A is that we get an odd number when we draw from the bag. Event B is that when we draw from the bag, we get a multiple of 3. And we're first asked to calculate the probability of A and the probability of B. Now, particularly when the events are described like it is odd, it is a multiple of 3, in the context of the problem that we can only select digits 1 through 10, I think it would be helpful to write out exactly how many odd numbers are there in this list. Exactly how many multiples of 3 are there in this original list. Take a moment to do so on your paper. So we know the odd numbers are 1, 3, 5, 7, and 9 within the list. The multiples of 3 start at 3. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. So in calculating the probability that whenever we draw one item from this bag, we would get an odd number, well, we know probability is always a fraction. The number of ways what we're looking for could occur divided by the total. Now the total number of outcomes is we could have selected any of these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 options. And of those 10 options, if we had selected any of these, 1, 2, 3, 4, 5 options, we would end up with an odd number, and that's what we're looking for. So take a moment to write out the probability of B, that when we draw a single number from the bag, we would get a multiple of 3. So we know as before we've got 10 options to choose from, and if we had selected any of these 3, which are multiples of 3, it would have met our criteria of being a multiple of 3, so the probability that B occurs is 3/10. So next up, take a moment to read this notation. How would you describe it in words? It is the probability that A intersect B occurs, and we know the intersect symbol is the same as the and symbol. So we would read this as the probability that A and B occur. So it's asking us, what's the overlap between these two sets? Well, the overlap between these two sets are the digits 3 and 9, because those two digits belong to both groups. So there's 2 digits that belong to both A and B. So the probability that A intersect B occur would be the 2 things that are from A intersect B divided by the 10 available options. Now our last problem is our new idea of conditional probability. We would read this as the probability that B occurs given A has already occurred. So one way to think about conditional probability is it's giving you extra information. Originally, we knew we were drawing one of these 10 items. That's what we knew for our first 3 problems. However, when they say the probability B given A has already occurred, what is A? A is that we have drawn an odd number. So what's happening here is, suppose we drew an item from the bag. We did not look at what we drew. However, a friend was next to us and they looked at it, and although they didn't tell us the number exactly, they did say, you drew an odd number. So since our friend told us this extra information, the fact that given we have an odd number, we know that whatever number I drew, it is one of our odd numbers, 1, 3, 5, 7, and 9. So what that does is that extra information, it kind of resizes our total number of outcomes. Since we've been told that we have an odd number, our new denominator of this expression, the total number of possible outcomes, is no longer 10, but 5, because we know the even numbers have been excluded. Okay, now let me go over that one more time just to try to make sense of it. See this given bar as given extra information. Originally, we thought we were just drawing from these 10, and any of the 10 could have been picked. However, since we were given that A occurred, where A is being an odd number, we know that whenever we selected one of the numbers from the bag, somebody told us that the number we selected actually was odd. So what that means is we weren't going to draw 2, nor were we going to draw a 4. So we did not draw 2, or a 4, or a 6, or 8, or a 10. Because we were told whatever item we drew, it happened to be an odd number. So instead of the 10 available options out there, we really only had 5 options remaining. Any of the 5 odd numbers. So the given information resizes your total. Now, of those 5 options, we want B to occur because it was the probability of B given A has already occurred, where A is the idea that we drew an odd number. And of that, what's the probability that we would get an item from B? So of the odd numbers, the multiples of 3, the multiples of 3 are 3, 6, and 9. So how many of those are in our available list? Well, we have 3, 6 was already crossed out because it was an even number, and 9. So 2 of the 5 outcomes are multiples of 3. So that's why the probability that B occurs given A is 2 divided by 5. So given that we've drawn an odd number, we knew we had to have selected one of the digits 1, 3, 5, 7, 9. That's why our total outcomes were 5. And of the possible outcomes, only 2 of them are multiples of 3. That's why we have 2 out of 5. So this was a method of calculating the conditional probability in terms of just kind of thinking about what happens given the new information. And this method works as long as you think through it carefully. Now let's calculate this using the formula as well, because both approaches work and you're just welcome to do whichever makes more sense to you. So looking at our previous page, we can copy down the formula. So from our previous page of notes, I've copied down this formula. The probability that B occurs given A has already occurred is the probability that they both occur divided by the probability of A. Now we happen to already calculate the probability that they both occurred. That was earlier and we found it was 2/10. We also know the probability that A occurs is 5/10. So the probability that B given A occurs is 2/10 divided by 5/10, and here we have to remember how to deal with dividing fractions. Remember the phrase, keep it, change it, flip it. Keep the first fraction, change the sign to multiplication, flip the second fraction. And then whenever it's fraction multiplication, it's top times top, bottom times bottom. That would be 20 over 50, or whenever you simplify to lowest terms, that's the same as 2/5. So we get the same answer either way, whether through thinking through the problem carefully or using the formula. Both methods are good. Feel free to use whichever makes more sense to you. So in our next example, it says, given a family with 2 children, find the probability of each event. Now, the only information we have about this family is that they have 2 children. So we need to think through what are all the possibilities of having 2 children. Well, we could have a family who had 2 boy children, or 1 boy who was born first, and then a girl who was born second. So the order that I'm listing the letters is related to the birth order. Or we could have had a family with a girl born first, and then a boy. And finally, we could have had a family with 2 girls. So there's 4 possible outcomes of birth order for a family with 2 children. And this is important, I think, to first just list out all the possible outcomes. That way we have something to look back towards. Now we're asked to find the probability. Let's do these 2 questions separately. That both of the children are girls. And then here's this new phrase that we haven't seen much before. Given at least one is a girl. So whenever we read this phrase of given, the way you should try to envision it is, originally all we knew was that the family had 2 children. But before we did our calculations to see what was the likelihood that they were both girls, somebody came up to us and said, oh, actually, I know that family, and at least one of the children is a girl. So we've been given new information that resizes our sample set. Since we've been told at least one is a girl, that means we should consider this situation, and this situation, but no longer that situation. Because somebody came up to us and said, I can't tell you exactly what the birth orders are, but I can tell you one of the children is a girl at least. So we know the only situations we should consider for this problem, given this new information, is that the children are boy-girl, or girl-boy, or girl-girl. So in terms of probability is always what we're looking for, which is both being girls. Out of our total possibilities, well, the total possibilities are 1, 2, 3 possibilities with at least one girl. And of those 3 possibilities, the only way we could get both being girls is this 1. So the probability is 1/3. Now we had the same starting point of the problem. It was a family with 2 children. But as we move to the next example, we kind of restart. So we originally had the 4 possible outcomes of having 2 children. And now we're asked to find again, what's the probability both are girls, given the new information that the older child is a girl. So think about how this new information, the older child is a girl, should resize our sample. So originally all we knew was that the family had 2 children. Before we started our calculations, somebody came up to us and said, oh, actually, the older child is a girl. I know that for sure. So that means we're not considering this because the older child's a boy. We're not considering this because the older child's a boy. The only ones that we are considering are these 2 because they have the older child being a girl. So as we think about our probability, the number of options that we're considering is 2 that meet our new given information criteria. And what we're looking for to occur is that both are girls. Of these 2, how many have both being girls? Just this 1. So our probability is now 1 out of 2. So these were 2 examples of conditional probability. And whenever you read things with conditional probability, try to see this given as new information that allows you to resize the total number of outcomes you're looking at. So next up we have a new definition, the idea of independent events. So A and B would be considered independent events if knowledge about the occurrence of one of the events has no effect on the probability of the other one occurring. Now, this entire sentence, if we translated it to mathematical notation, would be this statement. The probability of B occurring given A has already occurred is just equal to the probability of B. So the idea behind this is, remember, the given is giving you extra information. So you know A has already occurred. If the probability that B occurs given A has already occurred is still just the probability of B, that means the two events were independent because knowledge of A occurring does not affect B occurring. Now, said in another way, equivalently, if we had the probability of A occurring given B occurring, these two things would be independent if the probability of A given B is just the probability of A. Now in our class, there's only going to be two different ways that you would use this formula or this idea of independent events. Let's write down these two ways and we'll see this in our later examples. So the first way we might need to use this formula is if we're directly asked to verify if A and B are independent events. So if you are asked to verify that A and B are independent events, all you have to do is first calculate the probability of B. Then calculate the probability of B given A, and if they are equal, you know they're independent. So calculate the first thing, calculate the second thing. If they're equal, it's guaranteed to be independent by this mathematical idea. Now, another way that we might use this formula is if you are told A and B are independent. So at the beginning it says something like A and B are independent events. Then if we know they're independent events, we know that this relationship holds. So a very quick way to calculate B given A is we know it's just the probability of B. So it can make our calculations a bit easier. So in the first example, we're trying to verify their independence using this formula. In the second way we could be asked to use it is we're told they're independent, so we're guaranteed this formula works. So if we want to calculate the probability that B given A occurs, it's just as easy to calculate the probability of B. So in our next example, we have that a single card is drawn from a standard 52 card deck. So our sample space is the 52 possible cards that we could draw. And we're asked to find the probability of each of the given events. So event A is that the selected card is a face card. And if we think through our face cards, or we look back earlier in our notes to the table of different cards, we know that there are 12 face cards, 3 from each suit. Event B is that the selected card is a black card. Now we know that in a normal deck of cards, there's 2 red suits, 2 black suits. The red suits are the hearts and the diamonds. The black suits are the clubs and the spades. And in each suit, there's 13 cards. So we have our 13 spades and our 13 clubs. So altogether, there's 26 black cards in the deck. Now, if you would, take a moment and pause the video and calculate the probability that A occurs. And once you've done that, calculate the probability that B occurs. So take a moment, pause the video. When you're done calculating those two, unpause to check your work. So the probability that A occurs is if we draw a single card, how many ways could it end up being a face card from the standard 52 card deck? So we know the probability is the number of ways what we're looking for could occur. There are 12 possible face cards out of the total number of outcomes that we're drawing, 52. Now the probability that B occurs, B is the event that the selected card is a black card. we know there's 26 possible black cards in the deck out of the 52 possibilities we could draw from. Now, looking at this notation, read through how would we phrase it? We always read the P as the probability that this occurs. And what is this? It's the probability that B occurs given A has already occurred. So the idea is we've been given extra information. We know A has already occurred. A, which is selecting a face card, so think about it. We were drawing a single card from the 52 card deck. We haven't looked at it yet, but our friend sitting next to us says, oh, you drew a face card. Okay, so we know that we've drawn a face card. However, we don't yet know if it's a red face card or a black face card. So we want to know what is the probability that B occurs, that the card we selected is black, based on the fact you already know you have a face card. So remember, what does the given information do? It resizes your total number of outcomes, because originally we thought I'm drawing from one of the 52 cards. But our friend next to us told us, oh, actually you drew a face card. So we know specifically what we drew is one of the king, queen, or jack from the four suits. So we now know, since we've drawn a face card, there is only 12 possible face cards that we could have drawn. So our new total number of options is 12. And of those 12 face cards, we have 3 hearts, king, queen, jack of hearts, 3 diamonds, king, queen, jack of diamonds, 3 spades, king, queen, jack of spades, and 3 clubs. And of those, only the spades and the clubs are black cards, so of the 12 options, 6 of them would result in us drawing a black card. So that's our probability of B given A. We've been told that we drew a face card, so we resize our sets to only the face cards. And of those, how many ways could we have drawn a black card? And our final part of this problem is it says, use the results above to determine whether A and B are independent. So we need to see if A and B are independent. The way we check if A and B are independent is we first calculate what is the probability of B given A. Then we calculate the probability of B. And if 1 equals 2, the conclusion is they are independent. So let's see if this works out for us. So we already found the probability of B given A, that was 6/12. We already found the probability of B, that was 26/52. Now the fractions might not look the same, but we know fractions can have equivalent values even if they look different. So let's type both of these into our calculator and see what decimal value we get for each. So 6 divided by 12 is 0.5. 26 divided by 52, also 0.5. Since these are the same numerical value, we know A and B are independent, because knowledge about one does not change the probability that the other thing will occur. Now in this next box, we have 2 more formulas that we might find helpful in different circumstances. So if A and B are just any 2 events, we don't know anything more about them than they're just different events, then the probability that A and B occurs is equal to the probability that A occurs multiplied by the probability of B given A. So circumstances in which we'd use this formula are maybe where we knew the probability of A, we knew the probability of B given A, and we wanted to find the probability of A intersect B. then if you knew these two already, and if you know this formula, the probability of A intersect B can be found by taking this value and multiplying it by this value. So we should see this formula as maybe a way, if we have two of the three pieces, we can use this formula and then manipulate and solve for the missing piece. Now the next formula can only be used under a certain circumstance. You can only use this next formula if you know events A and B are independent. So keep that in mind. Only if A and B are independent can we use this formula. But if we happen to know A and B are independent, if we were told that, or we could show that based on reasoning like we saw earlier in this section, then the probability that A and B occurs is just the probability that A occurs multiplied by the probability that B occurs. But we can only use this in the specific circumstance that you know A and B are independent. Each year, Carrie adds to her book collection a number of new books. She has categorized each of her 20 books as hardcover, paperback, fiction, or nonfiction. The information is described in this table. Let's make sure we know how to read this table. So what we see here is the books are split between hardcover and paperback. And those are two distinct categories because the book's either hardcover or it's paperback. But within the hardcover books, we could have books that are fiction and nonfiction. So the way we would read this table is as this 3 is the intersection of the fiction column and the hardcover row, she has 3 books that are hardcover and fiction. Similarly, these 5 books are part of the nonfiction column and the hardcover row, so there's 5 books that are nonfiction and hardcover. Now taken together, the 3 fiction hardcovers and the 5 nonfiction hardcovers give us the 8 hardcovers in total. Okay. So if you saw this entry in the table, how would you describe it? What categories does it fit into? These are the 4 books that are nonfiction and at the same time paperback. Okay, so how many books are paperback in all? 12 paperback books. The 8 paperbacks that are fiction plus the 4 paperbacks that are nonfiction gives us the 12 paperbacks in all. Now if I ask the question, how many books are fiction? We would say, well, the fiction category, it has 3 hardcover fictions plus 8 paperback fictions gives me a total of 11 fiction books. So it says if she randomly chooses one of the 20 books, so imagine all the 20 books are in a bookshelf, she's going to pick one of them at random, what is the probability that it would end up being hardcover? Well, we know there was 28 books available to choose from, and in total there's 3 plus 5 equals 8 hardcover books in all. So 8 out of 20. Now let's read the next one. It says, find the probability that it's fiction given its hardcover. So this phrase, given its hardcover, is imagine at first she was going to select from the 20 books, she grabs one, and just by how you grab it, you can tell whether it's a hardcover or a paperback book. So once she's selected the book, she's like, oh, I know this is a hardcover book. So actually, I know that my probability is out of the 8 hardcovers. How many of those 8 hardcover books are fiction, which is what we're looking for? Of the hardcover books, only 3 are fiction. So the probability would be 3 out of 8. Okay, so now we restart the problem. Our next problem is again of these 20 books. Find the probability that it is hardcover and fiction. So I'd encourage you to pause the video and attempt this on your own. Unpause to check your work. So in this new problem, each of these three are separate, right? So once you go to the next one, it kind of resets the situation. She's selecting one of the 20 books at random, and we haven't been given any extra information here, so we can just assume that we're selecting one of the 20. So the total number of options available to us is 20. And what are we looking for? Hardcover and fiction. So we look how many books fit both the category of hardcover and fiction. There are only 3 books that are hardcover and fiction. So our answer to this should be 3 out of 20. So I've now written 3 new problems off to the side. I'd encourage you to write these down as well. And each of the 3 should be treated as separate problems. Once you complete one, you kind of restart, do the next one. So I would highly encourage you to pause the video and attempt each of these 3 problems. When you've attempted each of the 3 problems, unpause to check your work. So pause the video and work on these 3. So in this next one, we're asked, what is the probability that it is paperback given it is fiction? So we know this given phrase is giving us new information. Originally, all we knew is we were selecting one of the 20 books, but we've actually been told, hey, the book that you selected is fiction. So what this does is it resizes our total. We are now not selecting from the 20 books, but we're selecting from the 11 fiction books. And of these 11 books, we are asking who are paperback. So we look and there's 8 paperback books out of the 11. Okay, now we restart the problem. The next one says nonfiction given its paperback. So now in this new given information, we've been told the book is paperback. So you know for sure that the book you selected is paperback. So instead of the 20 possible books available, we are now looking at only the paperbacks, and there's 12 paperbacks in total. So our new total is 12, and of those 12 books, how many fit the criteria of being nonfiction? Well, we look, the nonfiction ones, there's only 4 nonfiction paperbacks, so our probability is 4 out of 12. Now our final question just asks us, what's the probability that whenever we select a book at random from our original setup, the 20 books, how many of those would be nonfiction? So in this case, we have no additional given information, so it does not resize our problem. Where in the original problem, you're selecting one of the books from the 20. How many of those books would be nonfiction? 9 of the books are nonfiction. So pay careful attention to the phrasing, the differences between and, given information, and just straight probability problems where we're not looking for anything, given anything else, just in the original situation, how many hardcovers were there? So as always, remember, if you have questions, you can contact me through our campus email or our online course platform.